All right, so yesterday we started 6.6 and we said that the test, God bless you, to determine if the inverse of a function is a function would be the horizontal line test. So this says use the horizontal line test to determine whether the inverse of the red relation is a function. So if I draw horizontal lines running through the red graph, do any of those horizontal lines hit the graph at more than one point? Yes, which means that the inverse of the red relation is not a function. Okay, so quick refresher, this is what we talked about. The vertical line test is to test if the one you're looking at is a function. And the horizontal line test is going to tell you if the inverse of that function is a function. And then we did example 2, right? We left off here, example 3. So use the horizontal line test to determine whether the inverse of each relation is a function. So if I were to draw horizontal lines through this graph, does it hit any of those at more than one place? No. So then the inverse is a function. Questions on that one? Okay, so finding the inverse. We've done this before, so recall that to write the rule for the inverse of a function, you can exchange the x and the y, and then solve for the new y. That gives you the inverse function, okay? Because the value of x and y are switched, the domain of the function will be the range of its inverse and vice versa. So if I've got my regular function, whatever this is, x plus 2, and then I've got my inverse function, so if I switched it, I'd get x. So y would equal x plus 2, switch it, x would equal y plus 2, and then solve for the new y. So this would be, oops, not y. This would be x minus 2. Those would be the inverses of each other. So the domain of the function on the left, and how do we find domain restriction? Is there one in this case? What are the two things you're looking for a domain restriction? Go back to the last section. So what happens if we had something in the denominator? The denominator can't equal 0, and what's the second case? Under a root. Are either of those happening here? No. So this domain would be all real numbers. There's no restrictions. So the domain for this function becomes the range for my inverse function. And vice versa. The domain for my inverse function. So what's the domain of this function? Are there any restrictions I have to worry about? No. So this would also be all real numbers. And the domain of that one is going to be the range of this one. So if you have a graph, it's probably easiest to determine domain and range from a graph. Domain is going to be your x values left to right. Range is going to be your y values bottom to top. But if you don't have a graph and you're finding the inverse, then find the domains of each, your original function and the inverse, and then the domain of each one becomes the range of the opposite function. All right, so this example says to find the inverse, determine whether it's a function, and then state its domain and range. So the first thing I do is find the function. So if this is my initial function, the cube root of x plus 1, to find the inverse, I would switch the x and the y, and then I want to solve for that new y. So how do I get rid of a cube root? Cube both sides. So I get x to the third equals y plus 1, and then subtract the 1. So f negative 1 of x is equal to x to the third minus 1. So that's the function's inverse. Okay, so that's the first part. The second is determine whether it's a function. So I can do this two ways. One is think about what my initial function looks like. So if I know what a cube root function looks like off the top of my head, which some of you may and some of you may not, a cube root function goes like this. So I can use that function and use the horizontal line test to determine if the inverse is a function. So if I drew horizontal lines through that function, would it pass? Yeah. So that's one way to do it. So then yes, this is a function. The other way is graph your actual inverse. So a cubic function looks like this. If there's a minus 1 after it, what's happening? What kind of shift is a minus 1 after the function? Down 1, so it would look like this. And then if I'm using to figure out if this function has an inverse, then I use the vertical line test. So if I pass a bunch of vertical lines through this function, do any of them hit the function at more than 1 point?
Yes.
Well, I mean, it's kind of hard to see, but that would be always, exponential is going to keep growing, so it's changing. So it actually does not. Okay? So that's the other way you can determine if it's a function. So based on the graph, if you're looking at the graph of the initial function, then you want to use the horizontal line test. If you're going to graph the function, the inverse of the function, then you would use the vertical line test. And then the last part of this is stating domain and range. So remember, the domain of my f of x becomes the range of the f negative 1 of x. So is there a restriction on the cube root of x plus 1? Can I cube root a positive number?
Yes.
Can I cube root 0?
Yes.
Can I cube root a negative number?
Yes.
Yes. So there is no restriction on a cube root. Remember, it's on a square root. So the domain of this function is all real numbers, which means the range of the inverse is all real numbers. Isabel?
So whenever you have like x cubed in your domain, you always have all the real numbers?
Yeah. The only restrictions are if the variable's in the denominator or if the variable's under the square root or an even root, right? Because I can take the odd root of any kind of number, but I can't take an even root. I can't take a square root or a fourth root of anything of a negative number. So the range, again, the domain of your initial function becomes the range of your inverse. And then the domain of this function, I can look at my new function that we just looked at, and I get x to the third minus 1. Are there any restrictions I need to worry about? No. So this is also all real numbers. Ian?
Why was that all real numbers?
The domain or the range?
The domain for the inverse.
The domain for the inverse. So when you look at the actual inverse, which is this one, there's no restriction. There's no variable in the denominator, and there's no variable under an even root. And if you think about what the graph looks like, remember I drew over it a bunch, but it was this. Whoops-a-daisy. It was that. My x values are going to be negative infinity to positive infinity, and so are my y values, which would be the domain and the range. Fine. So find the inverse of f of x equals x to the third minus 2, and then determine if it's a function and state its domain and range. So start by finding the inverse. Remember, switch your x and y and solve for the new y. All right, so start by rewriting your function with the y, switch the x and the y, and then solve for the new y. So my inverse is the cube root of x plus 2. Raise your hand if you got that far. Questions on how to get that far if you didn't? So switch the x and the y, solve for the new y. That's the first part, okay? Then it says determine whether this inverse is a function. So again, you can think about what your actual graph looks like. Use the vertical line test on this new graph, or use the horizontal line test on your initial function. So that initial function is again a cubic function. This time it's shifted down 2 places. It looks like this. Would that pass your horizontal line test? Yeah, which means that this is a function. And then it says state its domain and range. So the domain from my initial function is what? Domain of f of x, or x to the third minus 2. All real numbers. Which means the range of my inverse is all real numbers. And then the domain of my f negative 1 of x equals the cube root of x plus 2 would be what? All real numbers. Questions so far?
Is there any possible way to find the range of the initial function?
Without a graph, it's just not as easy. You basically have no restriction unless your graph has some sort of restriction with a square root or your absolute value where it's pointing up, that kind of thing.
Okay.
So if you can graph it, then just look for your y values.
Okay.
But by looking at the equation, you'd have to like figure out, okay, is there a restriction on x? That would be my domain. And then if I had those values, what kinds of y's would I get out? Which is a little bit trickier. It's easier to do it the other way. Find the domain of each function, and the domain of your initial function becomes the range of the second function. All right, so then there's a one-to-one function. When both the relation and its inverse are functions, so this would pass both the vertical and the horizontal line test, then the relation is called a one-to-one function. In a one-to-one function, each value of y has exactly one value of x. So there's not 2 x's for a y or 2 y's for an x. There's 1 to 1. So think about how you get like 2 x's for the same y. So if I've got a graph or 2 y's for the same x. If I've got a parabola and my y value is 1, I have 2 x's, right? I've got positive 1 and negative 1. So this is not going to be 1 to 1. If that's turned on its side, now I only have 1x, but I have 2 y's. So that wouldn't be 1 to 1 either. So any kind of absolute value or squared function in which you'd have 2 values would not be 1 to 1. They have to pass both the vertical and the horizontal line test. And a test for identifying if they are inverses of each other is using the composite function. So if I ask you if f of x and g of x are inverses of each other, then you can use the composite function. F of g of x should give you just x when you simplify it, and g of f of x should give you x when you simplify it. And that's how you can identify if two, based on the equation, if 2 equations are inverses of each other. So you're checking for 2 things. 1, is it 1 to 1? 2, is one function the inverse of the other? And you have to do the composite functions of those. So the question just says determine by composition whether each pair of functions are inverses. So f of x is 3x minus 1, and g of x is 1/3 of x plus 1. So the first thing I'm going to do is find f of g of x. And I want my answer to be x. If it's x, then at least that's 1/2 the way. So how do I find f of g of x? This goes back to your composite functions.
Replace x in f of x with 1/3 x plus 1.
Good. I'm going to take whatever g of x is and plug it into the x on the f of x. So this would be 3 times 1/3 x plus 1 minus 1. Good. Distribute the 3. So 3 times 1/3 x plus 3 times 1 plus 1. What's 3 times 1/3? 1. These cancel. I just get x plus 3 minus 1. Just kidding. Minus 1. And I get x plus 2. Is that x?
No.
No. So I already know that these are not inverses of each other. If they were, then when I did f of g of x and g of f of x, my result both times should be x. If it's not, then they are not inverses. Ian.
How do you know to check if it's supposed to be x?
It'll ask you, like the directions say determined by composition, that's what that means.
Well, no, but I'm saying, okay, when it says that, like, why does it have to equal just x?
That's what will happen with two inverses. You get y equals x. So the x of one equals the y of the other.
Because f of g of x is y.
F of x itself is y. So you're saying the y values of f of x should equal the x values of g of x, which is how you would know it's an inverse. So this is, your test is this composition function.
So if one of them is not x?
Then it's no. Yep, they both have to be x. Let's try one. So it says determined by composition whether each pair of functions are inverses. And this time it says x cannot equal 1 or 0. Why do you have that?
Because the denominators.
Good. It's giving you the domain restriction already, okay? If they were 0 or 1, then those would be undefined. So let's start with f of g of x. So I'm taking this and I'm plugging it into that x. So 1 over x plus 1 minus 1. I get 1 over x, a positive 1 and a minus and a negative 1 cancel out. And what happens when you're dividing by a fraction?
Flip 1 and multiply.
Good. So this is 1 divided by 1 over x. I do keep, change, flip, and I get just x. So the first one worked. Now you got to check the second. G of f of x. So this time, f of x is getting plugged in to the x of the g. So 1 over x minus 1 plus 1. Here's where it gets a little bit trickier because I've got a fraction with a fraction inside of it. How do I combine these two? What would be the like denominator?
But the fraction?
But you'll still have a fraction within a fraction, though. You can do it that way. That's one way to do it. So you're saying 1 over x minus 1 plus 1 over 1. That's what you're saying? Yeah, you can do it that way. You'll still have a fraction within a fraction, though, which you can do keep, change, flip. But there's another way, right? Like, how do I combine these into one fraction? What would be the least common denominator? X minus 1. So this would be x minus 1 over x minus 1. So I'd get 1 over 1 plus x minus 1 over x minus 1. The 1's here cancel. I get 1 over x minus 1. Keep, change, flip. So it would be 1 times that. Is that x? Does this equal x? No. So even though the first time worked, the second time did not. So they're not inverses. So let's go back to something a little bit easier. Let's go back to that first example that I showed you where we found. All right, so same question. Show that or determine whether f and g are inverses of each other using composition. So a little bit easier. F of g of x means take g of x and plug it into the f of x. So x minus 2 plus 2. And what happens here? These cancel and I get f of g of x equals x. So the first one is good. Then do g of f of x. So this time I'm taking this and I'm plugging it in here. X plus 2 minus 2. And what happens? The 2's cancel out. So these are inverses. So test we haven't made yet. Quiz are maybe not as easy as this, but not as complicated as the last ones. Yeah, a little bit more middle of the road. Okay, but the concept is the same. You're going to have to do composite functions just by themselves, which was the last section, and then you're going to do composite functions to show that they're inverses. But it will say, like, show using composition whether or not they're inverses. And either they're both x's or they're not. If they are both x's, they're inverses. If they're not, then they're not. Okay. Questions on any of 6.6? All right. So you can